First, I'd like to introduce the METEOR project, which enabled the creation of this video. METEOR stands for Modelling Exposure Through Earth Observation Routines and was funded by the UK Space Agency through their International Partnership Programme as part of the Global Challenges Research Fund. The METEOR project aims to develop innovative application of Earth observation technologies to improve understanding of exposure. Natural hazards have had escalating impacts, which are contributed to by an increasing exposure of population and assets. However, a major challenge when making disaster risk management decisions can be a poor understanding of the distribution and character of exposure. Robust quantitative methods are required to justify these decisions, and in this project, we are looking at the use of Earth observation technologies within that context. Within the METEOR project, there is also the aim to share knowledge. This video is produced as a part of a series of educational videos to enable the use of METEOR products and data.
So next, the value of Earth observation. This is an Earth observation project, so we'll be talking about the role of EO data and how we use that. Global population data sets are really very valuable, but they have to be used. You really have to take a close look at them in the country or the region or the city that you're looking at to make sure that it's accurate in that location and doesn't need to be adjusted. And we'll show some examples of the variants. Global urban, rural, or urban intensity data sets are something that are being generated more and more frequently. An urban intensity data set will just give you the percentage of built up in an area, whether it's 100%, 50%, 10%, 20%, and so forth. That can be used to infer the number of buildings throughout an area where you're spreading them from the census tract or the province or whatever level you've got the census data at quite effectively. Just basically a way to distribution there. Again, those don't always work great. Sometimes they go haywire in mountainous areas, but a very nice addition to the interpreted EO data sets, I would call them. Also, that that urban intensity can correlate quite nicely with structural patterns. Segmentation of development patterns, I'll talk about that in a little bit more detail. Building footprint extraction, average building size, again, getting that down into that information about housing units and how much area to associate with a person when you're spreading this data. And then I'll talk about challenges in some emerging research. All right, so global population data sets. Here's an example from PopGrid, which I mentioned out of CSUN, NASA Center in New York, associated with Columbia University. They did some great work here. Actually, they put this together specifically for this use case, trying to evaluate the applicability of population data sets for hazard purposes, where you're able to go into a specific area and see multiple data sets of that area and assess how accurate that data set is for you. And as you can see here, I don't have the legends on here, but there's quite a bit of difference between these data sets. And it's essentially how they've done their own interpolation from the data set that they had, which might be associated with, or if they've done it, with an administrative unit to a more localized region. So if you look up in the upper right-hand corner here for Kathmandu, you can actually see the admin zones that gridded, but that were the data was provided by. So in the upper right hand of the upper right hand, for example, in the mountainous areas, you can see, and that's because in this data set they don't do any interpolation based on the remote sensing data set. That's just an aggregated global product that they distribute so that others can, and that's why it's called unadjusted, And that's why others can use that to essentially come up with an interpolated product. And all these other ones, the GHS, WorldPop, and Landscan, are different, represent different methods of doing that interpolation. And you can see in some places where there hasn't been any indicators of human development, they've essentially interpolated that very, very evenly to a low number, or you can use the word smeared rather than interpolated. And that's why you have these sort of large orange blocks surrounded by these white zones, which is, by their opinion, areas that are unpopulated. And you can see there's a much stronger density along roads, and then in the city of Kathmandu itself. And if you go down to WorldPop, it looks a little more like the GPW data. You can still see the administrative units a little bit. There is a sort of a floor in the interpolation, and there is no white spots. And the lower right Landscan is essentially somewhere between the two. Does not distribute as much population along roads. So, in the process of coming up with the level 3 database for Nepal, we had to take all of these data sets and figure out what we thought was the most appropriate methods where, and came up, eventually with our own interpolation algorithms to do a lot of this. But if you're using one of these right off the shelf, you have to look at this. OSM data is really good here too, where it's complete, and figure out what is the most accurate for your area and for your purposes. All right, again, drilling down into that global urban, rural, or urban intensity data sets. Here's 2 examples, again, from Nepal. Here's southern Nepal, right there on the border of India. A really great area to look at. This is in a valley. The mountains are up here. This is just along a river, I believe, an area where you have quite a bit of distribution of population, and then just a real sort of speckle of farms and villages outside of that major core development. A nice challenge to be able to identify those smaller communities, and I think we were able to do it. This urban rural intensity, I think this is the GHS data, didn't always do a great job, but sometimes if you're trying to infer where you've got different development patterns, for example, these areas that are black speckled throughout here amongst the small settlements are very likely to be very rural, and in these settlements have a little a smaller a different type of structural development, so that you can use that to essentially develop your patterns. And here's what it looks like for Kathmandu. I'm sorry, it looks like it's got a different color scheme here, but you can see quite clearly where you've got development and where you don't. So now I'll go through an example of the process of using EO for segmentation of development patterns. This is a use case for Beijing, China, where you might have data by these very large zones. That might be the finest population data that you're able to have. And your question might be, I know where my exposure is with respect to those zones, but how does it fit with respect to these flooding zones, right? And obviously, the data that you have that's aggregated up at that higher level doesn't really answer the question of what lies within those water patterns. So here's an example of just how you would use that segmentation to solve that type of a problem. A little bit different than the risk problem that we have, but very similar, same tool set. So here's another, just a Landsat image of Beijing. You can see we've circled some industrial areas. And you can use training data sets to basically run an interpretation algorithm over the whole country. It's called supervised classification to identify whatever the development patterns that you have in these zones. Typically, there's going to be a lot of speckle, a lot of noise, so it becomes more accurate if you aggregate it up a bit. And we've done that here, I think. So this is probably the 15 arcsecond level, and you can see these patterns throughout the city. So as you get to the older city core of Beijing, you have more mid-rise structures. The higher-rise are actually in the newer areas and pockets outside of the city, and that's interspersed around following that with more single-family residential, or at least we're calling it here. And then the idea here is that you take those development patterns and you're able to do some sampling. This is actually from another country, but you're able to do some sampling within there to figure out what percentage of buildings are in what structural classification. You can map them to a vulnerability function. Building footprint extraction. This is a more standard, typical use of remote sensing data. It's very powerful in one sense, but not so powerful in another sense. There's loads of information. There's loads of papers and so forth that you can find online about what algorithms to use with this regard. Feature extraction modules, I think, for ArcGIS, or they used to be anyway. Sort of canned applications just geared specifically towards taking EO data and doing building extraction. And if you have high resolution data at your disposal and your area is small, it's definitely worth considering this type of operation. But it can be challenging, and I think these two images here illustrate some of those challenges. So the image on the left here is a SAR data set, and this is actually an elevation data set for Los Angeles. And you can really see the development patterns quite well. These large blocks here in the upper left are actually studios, movie studios. And as you have this lighter speckle here, these are actually the residential areas. So it does an okay job at this resolution of extracting out those large buildings. The other ones not so much, but it gives you an idea of what the area are and certainly where they are for development pattern purposes. Here's a similar method that's done from segmentation, not elevation, but segmentation, which is just a supervised classification that's done in any standard remote sensing package with optical data. I believe this is, in this case, looking at building damage in Port-au-Prince, Haiti, following the event. But regardless, these orange boxes here represent the footprints of buildings. If you were to square these off, sometimes there's algorithms to square these off to interpolate through the green areas, which in these cases are trees. It gives you a little bit more accurate of an estimate. And you can put a lot of work into doing this type of extraction, and if your area is small, it could be worth it. Certainly to try to get the building area to person proportion for different samples, it can be worth it. But what this is good at doing is telling you the total area of the building footprint. And by footprint, I mean the area as shown on the ground of the first floor, the square footage associated with the first floor. But it doesn't tell you how tall they are. So there's that adjustment that still has to be made. It can be made through sampling or expert opinion as well, or just based on the development patterns of what you know of an area. But it's not very good at telling you the count of buildings. And if you look carefully, you can see how a lot of these orange areas sort of smash into each other. Some of that might be due to damage. Some areas it works quite well. They're very distinct. And others, they bleed into each other in a way that you wouldn't be able to get a good count of the buildings. Now, I would argue that square footage is more important than count when you're talking about your losses. but it also tends to work better for some roof types than others. And um, a lot of roofs look like cement. So if you look carefully, there's some of these square red zones, which is probably characterized as cement type material that you also see crisscross in some of these parks and some of these shadows. What we've got here, this large building on the right with the courtyard in front of it, is actually the palace, the Port-au-Prince Palace. It could be some damage there, but it's got these sort of red areas, which is interpreted as a different material. And if you were to count up all the orange speckles there, you would have much more than one that we can see with our eyes is the building. So in general, for loss estimation purposes, it can be powerful to have some of this data to give you a sense of the people per building area equation. But it's not something that you generally want to run over very large areas, and it's not something that you typically want to use verbatim as a loss result for level 5. It's something that you want to use to make your assumptions for a level 1, 2, 3, or 3 type analysis. I would argue that the better way to do it is to to basically define your development patterns that you're seeing in a country that you can start to classify with EO data, and then just have someone go in and digitize those. It's not too much work. It gives you a better answer, gives you a firm count, and allows you to spend a lot less time wrestling with finicky algorithms. But other people prefer to do it the other way. All right, some of the challenges and emerging research that come out of the EO, low light. I think I've mentioned a lot of these before. Low lighting, particularly in large parts of Africa, and the villages won't have lights to be able to detect them, can make it more challenging. That doesn't impact the optical sensors that are, standard luminance optical visible bands, which can still be used to detect these things, but depending on the material, it can still be quite complicated. Under tree canopies is pretty much impossible. Cloud cover can be a real drag, something that you have to account for and look at. Mountainous regions. If you're looking at those visible bands, a lot of times the patterns that are made by mountains, the real bright exposed rock and the sharp edges look like what AI determines is probably a man-made material, and you'll see that in a lot of the global products. They can account for those with a DEM and just sort of strip them out, but then that also strips out settlements in the mountainous region. So you have to really account for that and look carefully, and that's something that we did quite a bit of in Nepal for the level 3 data. And indigenous materials. Sometimes I'm thinking in BAM, Iran, for example, there was a lot of the construction was made out of the material, and from the sky it was the same color. It was the same color as the streets and the same color as the yards. So if color is not an indicator, then you have to basically use pattern recognition type stuff. AI can be useful there, but it's, again, something you have to roll up your sleeves and do. Emerging research, new sensors, a lot more SAR data is coming online, a lot more high resolution data is coming online, so figuring out how to use that effectively. A lot of building footprint data is being released by Microsoft and others, and the OSM data. All of that stuff can really help if it's used correctly. You have to be very careful in how you do that. I can overestimate exposure if you're not careful, or underestimate it. But it's definitely a tool that you can use in your toolbox. as well as data from Street View and UAVs. AI run over these images and video streams to detect building types, for example, is something that a lot of people do, but I would argue